Hello, Math 1341 Calculus 1 students. We're going to go over two problems from optimization. This is a wonderful and yet challenging topic. Both of these problems come off previous final exams, so they're wonderful extra practice for us. We will get started with the first one. A company is producing a cylindrical metal can. We are given its volume. We're given information about the costs of the material. And then we want to find the minimal cost of the can. This is a minimization problem. First of all, let's draw a cylinder. In all of these problems, I recommend you start by drawing a picture if it's applicable. Then what are we given? We're given volume. Well, maybe let's put a little radius and h. If we have radius r, height h, well, the area of the base is pi r squared, and then we multiply by the height to get the volume. So we are told the volume, which is pi r squared h, equals 32 pi. Now you notice this is an equation, and this is our constraint equation. We're not trying to maximize or minimize volume. It's given. So this is our constraint equation. Now, we're trying to find minimal cost. So let's write a function of cost. Initially, this function will be of both r and h. Okay, well, let me think for a moment about this side part. It costs 1 cent per square inch. So in my picture, I have taken the side and unrolled it. And then you notice the h is still h, but this is 2 pi r. It's the circumference of the circle. So that's going to help us here. To get the cost as a function of both r and h, well, on this part, which goes all the way around my can, the area is 2 pi rh. And then the cost is 1 cent per square inch. And then the top and the bottom both cost 2 cents per square inch. This area is pi r squared, and this area is also pi r squared. So we have 2 pi r squared. That's because we have a bottom and a top, and then we multiply by the cost, which is 2 cents per square inch. So this is our cost as a function of both r and h. Maybe I'll take one step here. This is 2 pi rh plus 4 pi r squared. This is our objective function. Now, what we need to do is get this cost entirely in terms of one variable. So we work with our constraint equation. Probably it's easier to solve for h in terms of r because I don't have to take any square roots. So you notice I can divide by pi on both sides of the equation, and then I get h is 32 divided by r squared. This is the relationship between h and r that comes from my constraint equation. Now, I'm going to write cost entirely as a function of r. I have 2 pi r times h, which is 32 divided by r squared. And then I have 4 pi r squared. We have 64 pi r to the minus 1, and then plus 4 pi r to the 2 r squared. And this is it. Now, maybe I'll underline this and highlight it because this is important. And we want to minimize the cost of the can. So we are minimizing this. We can think about the domain here. We want to minimize on, well, let's see. R cannot be 0. That wouldn't make a can. And similarly, well, R can be any positive number because we could always find an h that satisfies this and make a can. So we are minimizing this function on the open interval from 0 to infinity. Okay, this was the hard part. This is the setup of the problem. Now we're ready for derivatives, critical points, things like this. So we take the derivative, c prime of r. This is minus 64 pi r to the minus 2. And then we have plus 8 pi r. Critical points are where the derivative is 0 or does not exist on this interval. Okay, well, does not exist. You see I have an r to the minus 2. This will just happen at 0. That's not in my interval. So really, I'm just interested in where the first derivative is 0. Well, what I'm going to do is just move the minus 64 pi r to the minus 2 to the other side. I will have 64 pi r to the minus 2 equals 8 pi r. And at this point, I need to move to the next page because I'm about out of space. So let's copy this and we'll move to the next page. Now, I can divide both sides by pi, and I can also divide both sides by 8. So I will have 8 r to the minus 2 is r. Now multiply through both sides by r squared, and I get the following. I get 8 is r cubed. This is something we can now solve. R will just be the cube root of 8, which is 2. So we have exactly one critical point. What this means, having exactly one critical point, and we're looking for a global extreme value, is we could just use, say, second derivative test to make sure we have a min. So let's go back and copy my first derivative, which is here. Maybe I'll put this. This is the only critical point. But we must verify that, in fact, we have a minimum. This is quite important, the verification. So let's take the second derivative. What do we have here? We have 128 pi r to the minus 3, and then we have plus 8 pi. And then evaluate the second derivative at 2. So we have 128 pi, 2 to the minus 3, and then plus 8 pi. Certainly this is positive. This tells us my cost function is concave up. And you notice concave up, we have a min. So in fact, we do have a minimum. Wonderful. Well, the final step is to read the question again. It says this: what is the minimal cost of the can? This is always the final step. What are you reporting back? We know the R, we have verified it's a minimum, but then we want back the cost. And the cost as a function of R is right here. So let's copy this and put it on the next page. I'll also put this in gray. The minimum cost, which is our final answer, we evaluate C of 2, which is 64 times pi times 1/2 plus 4 pi times 4. So altogether, you see, this is 32 plus 16, 48 pi. This is a cost. If you want it as approximate decimal, okay, that's usually how we look at cost rather than seeing a pi in it. So I will leave my answer like this. I would also accept 48 pi because this is also correct. Number 2, here we want to build an open box with a square base, and we're given the amount of cardboard that we have. We want to find the dimensions to maximize the volume. This is a different question. In fact, it's quite similar in that we have some geometric shape. But in this question, we're trying to maximize volume. We are not given volume to begin with. But we will get started and draw a box. Here's my box, and let's pretend that base is a square. I tried my best, but we label x, and then we have some height y. Now, find the dimensions that maximize the volume. First of all, we can write what the volume is. The volume is x squared y. And this time, this is my objective function. It is not an equation. And in fact, this is what we want to maximize. So this is my objective function. And now we have to write down the constraint equation based on what's given. Oh, my box has an open top. Okay, very nice. Now, we have 2,700 square centimeters of cardboard available. The bottom is x squared area. And then you notice I have 1, 2, 3, and 4 sides, but they're all the same. They're all x by y. So I have 4xy. This is the surface area. This is how much cardboard I need, and I'm not including the top. And this will be 2,700. This is my equation that relates the variables. This is my constraint equation. Fantastic. Well, we use this, right? We use the constraint equation to solve for one variable in terms of the other. And here I think that y is going to be easier to solve. So how can we do this here? You notice that 4xy is 2700 minus x squared. And now just divide everything by 4x. This would say that y is 2700 divided by 4x, and then minus x squared divided by 4x. One more step in simplifying this. This is 675 divided by x, and then we have minus x over 4. At this point, let's go back to our volume. We will write this entirely as a function of x. This is x squared times y. Maybe I'll just copy what y is. When we multiply through by x squared, here I have 675x. And then I have minus 1 over 4 times x cubed. Well, let's think about what we're doing here. First of all, question says maximize the volume, so we will be maximizing this function. And then we can think about the open interval. X must be positive. Now, because y must be positive, the largest x squared can be is 2700. And so this would say here. We are maximizing on an open interval. Now is the time for calculus. Let's take the derivative, look for critical points. Here I get 675 minus 3 over 4 x squared. This derivative is defined on the whole real line. Really, the critical points will come where the first derivative is 0. So let's solve here. We get 3 over 4 x squared equals 675. Now here's where I'm going to copy and paste, move to the next page. These problems take a little bit more writing than just one screen's worth. So we paste. When we take 675 and multiply by 4 over 3, we get 900. Technically, just solving x squared is 900, we have two solutions. We would have x is 30 and minus 30. However, this one is not in the domain. We cannot have a negative length of a box, so not in the domain. And so the conclusion is we have just one critical point. It's right here. This is the only critical point on our open interval. Okay, next step. We know we have a critical point. We must verify that we have, let's see, a maximum, because find the dimensions that maximize the volume of a box. We need to verify we have a max here. And we can do this using the second derivative test once again. So let me just copy and paste. We calculate the second derivative. We have, let's see, 0 minus 3 over 2x. And the second derivative at 30 is minus 3 over 2 times 30, which is certainly negative. This says my volume is concave down. And we draw a picture, we have max. We have a maximum. Wonderful. This is what we were looking for here. The final part of this is to reread the question and see what we're reporting back. We want dimensions. Well, we know the x, 30, 30. And so we just need to solve for the y. This will be the third dimension of this box. And they're related, well, here. So maybe I will copy this part. This is how we get y from x. So copy. At x equals 30, y would be 675 over 30 minus 30 over 4. Now, we want to write this as an integer simplified fraction. Both 675 and 30 are divisible by 15. So this first term is 675 over 15, which is 45, and then divided by 30 over 15, which is 2. And then you notice 30 and 4 are both divisible by 2. So this is minus 15 over 2. We left with 30 over 2, and this is an integer. This is 15. So the dimensions, maybe I'll do this here and underline the dimensions. We have 30 by 30 by 15. This will give us the maximum volume subject to this fixed amount of cardboard. So this was the end of these optimization extra practice problems. Thank you so much, students. I hope this was helpful for you.